He is Jorge Delgado. He is a PhD student from the Aveiro gravitational group with Carlos Herdeiro and Eugen Ratu, and he was working on Kerr black holes with scalar hair, axiom-Boson stars, rotating boson stars, and this kind of exotic matter. So he's going to introduce us his new paper. Well, one of the latest papers about this kind of rotating geodesics and how the matter around these stars moves. So it's a pleasure having him here, and as you want, you can start.
Cool. So thank you very much for the invitation. It's quite good to be here and physically be here after the 2 years of COVID. So I'm Jorge Delgado. I'm a postdoc now in IST in Lisbon. Unfortunately, this is only a temporary position for a few months, so I'm still working on trying to find a better postdoc position. So if you know any new position, or if you will open here one, please let me know so I can try to apply. So thank you. So as George also said, I'm here to talk about timelike cyclic orbits around generic ultracompact objects. This is a work, it's almost a year now, that I did with Professor Carlos Herdeiro and Dr. Gina Hadun. And well, the first thing that you can ask is why study cyclic orbits in general? And most of you know that cyclic orbits are associated, for example, with the shadow of a black hole, with accretion disks, and so on. So it's quite important to study this type of geodesics. And there are two types of orbits that are quite important, mainly the timelike cyclic orbits and the null cyclic orbits. The first one is associated with how matter moves in the cyclic orbits around a given object. So it's associated for accretion disks and so on. The null case is more associated with light rings, the well-known light rings, then is associated with the shadow. So within the first type of cyclic orbits, the timelike ones, there is a particular orbit, which is known as the innermost stable cyclic orbit, or ISCO for short. That by knowing this orbit, you can associate it with several phenomenology quantities, such as, for example, the inner edge of an accretion disk, the cutoff frequency of the emitted cyclotron radiation associated with accelerating charge on the accretion disk, as well as the cutoff frequency of gravitational waves produced by an extreme mass ratio in spiral, or M-ring. Regarding the null cyclic orbits, we have the well-known, as I said, light rings. And these are associated more with the inner edge of a shadow, or even the real part of the frequency of quasi-normal modes. So regarding the light rings, there are two well-established results in the last years. One of them is from this PRL, where the authors showed that for ultra-compact horizonless object, so an object without an horizon, and that is ultra-compact in the sense that it possesses light rings, those light rings only come in pairs. So it can be 2, for example, or 4 or 6, and so on. And these two light rings that appear, this pair of light rings, the inner one is always stable, the outer one is always unstable. The same authors, some years later, showed that for the case of a black hole, the black hole always has at least one unstable light ring outside of its horizon. It can have more, but the other ones only come in pair as well. So these are quite two remarkable results because they are quite general, but they only talk about the light rings. And here I'm a bit more interested in trying to see if this structure for the light rings also implies some structure for the timelike cyclic orbits. And that's why I will show you in this first part of my presentation. In fact, there is some structure that appears. So I will explain these two diagrams. So in my second part of the presentation, I will basically show that exactly these types of structures appear for numerical solutions that we obtained throughout my PhD, as George said, and also we'll talk about the efficiency. I will explain what efficiencies mean at a later time. So let's start with the first part, the structure of cyclic orbits. So in the beginning, you start with a very generic spacetime that is stationary, asymmetric, asymptotically flat, and in 4 dimensions. With the symmetries and some gauge choice, you can write this very generic line element, which basically represents a rotating object. And we also impose that there is a Z2 symmetry, such that the equatorial plane is a total geodesic submanifold, and it's within this submanifold that we look for the cyclic orbits. One way to find them is by considering the effective Lagrangian of a test particle, writing in this way, where this G might be -1, 0, or 1 if you consider time-like particles, null, or space-like ones. Then, with the symmetries associated to the two killing vectors, you can define the energy and the angular momentum of the test particle and rewrite the effective Lagrangian in this way, where these A and B functions are given here. And I note here that this B function is always positive outside a possible horizon. Then you can redefine everything and find this effective potential in this way. And you do this because now to find the cyclic orbits, you only have to say that the potential and its first derivative must be equal to 0 at the given cyclic orbit. This means that we have to solve these two equations simultaneously. And by doing that, you can find the cyclic orbits. Then you can look into the radial stability of these orbits by looking at the second derivative of the potential. And if it is positive, then you have an unstable cyclic orbit. If it is negative, then you have a stable cyclic orbit. Furthermore, since we are considering a very generic stationary spacetime, when you try to solve these equations, we will find a pair of solutions in which one of them corresponds to prograde orbits and the other to retrograde ones. Now, with everything defined, you just have to choose what type of particles they are considering. So we have to specify basically this C here. So for light, this C is equal to 0. And as I said before, these are the well-known light rings. You can find them by solving the two equations, these two equations. The first one gives an equation for the inverse impact parameter, which is basically the energy over the angular momentum of the particle. And the second one gives a radial coordinate of the light ring. You can then look into the radial stability by solving this equation and see if it is positive or negative to see if it is unstable or stable. You can then do exactly the same for time-like particles, but now the results are a bit more complicated. But they can be simplified a bit by introducing the angular velocity of time-like particles. With this equation and with the first one, the potential equal to 0, you can find an expression for the energy and the angular momentum written in terms of the metric functions and the angular velocity. We also have this beta function, this equal to this, and it is highlighted in red because in the next slide will be important. Then with the second equation, the first derivative of the potential, you can find an analytical expression for the angular velocity only written in terms of the metric functions, where the C function here is given by this expression. Then again, you can look into the radial stability and you solve that equation, you see if it is positive or negative, to see if it is stable or unstable. So now that all the work is well structured and laid down, I can now focus more on the main result that I want to show you here. So the main result is that the radial stability of a light ring determines both the possibility and the stability of radial time-like cyclic orbits around the light ring. In order to show this, you have to realize that when the beta function that I introduced in the previous slide is equal to 0, we are exactly on a light ring. This can be shown by taking the expression for beta. You can go back in the other side and see, and putting equal to 0. And what this means is that the angular velocity at this cyclic orbit is basically exactly the same as the inverse impact parameter in that cyclic orbit. This means that it solves the potential for light, the light rings, equal to 0, the first one. Then, in order to see that this is exactly a light ring, we also have to show that the first derivative for the null particles is also equal to 0 on this cyclic orbit. You can write you can go back and grab the expression. Then using this first result and the definition or the equation that you obtained before for the angular velocity, in fact, this is always equal to 0. So if this is equal to 0 as well as the potential, then we are exactly on a light ring. This means that when beta is equal to 0, we are on a light ring. Now you may ask, why did I did this? Why do I try to find when beta is equal to 0? Well, this is important because if you go back, the energy and angular momentum of a time particle goes as 1 over the square root of beta. So the first thing you can see is that on a light ring, this diverges. However, more importantly, there is this square root. So if you go to a region close to the light ring, if beta is positive, or if beta is negative, then the energy and angular momentum of the time particle will be complex. So you don't find time-like cyclic orbits there. In fact, what you find is there is a region for space-like cyclic orbits. But if it is positive on that region, then the energy and angular momentum are real, so you can find time-like cyclic orbits. So you can try now to see on these regions close to the light ring when you have beta equal to bigger than 0 or smaller than 0. For that, you can do a Taylor expansion around the light rings. So in first order, you only have the first derivative of beta, since beta at the light ring is equal to 0. So by computing that derivative and simplifying everything, you get this result, where basically we have here this square root. So what comes out of a square root is a positive number. So this is positive. What comes out here. L square is also a positive number. So the sign of beta only depends on the stability of the light ring and if we are radially above or below the light ring. So in order to be a bit more easy to understand, let's look into a diagram. So imagine that we have an object with an unstable light ring. So what happens in that case is that the inner region of the light ring is a region where you don't find time-like cyclic orbits because beta is negative. But the outer region is the one where you can find time-like cyclic orbits because beta is positive there. If you have a stable light ring, basically it's the opposite. So the outer region now is the one that you don't find time-like cyclic orbits, and the inner one is the one that you find time-like cyclic orbits. So these two results are quite interesting, or at least for me. But you can go a bit further. You can try to see what type of stabilities do you find on this allowed region. For that, you write the radial stability or time-like cyclic orbits. So this is the same expression as before, but now I specified the expressions for the energy, the angular momentum. So it's a bit more convoluted, but I did this because if you go to a region close to the light ring, beta goes to 0. So this first term starts to diverge, either to plus infinity or to minus infinity. And this second term is always finite. So close to the light ring, this term doesn't affect anything. So you can look only to this first term. Then, if you look into this denominator, the b function, as I said in the beginning, is always positive. And the beta one, we are looking at this region where you can have time-like cyclic orbits. So we are on the region where beta is positive. This means that this denominator is always positive at the regions that we are looking at. So this first term diverges to plus or to minus infinity if the numerator is either positive or negative at the light ring. So you can compute the numerator at the light ring, and it simplifies quite a lot just to this quantity. And as you can see, these two quantities are square, so they are positive. So the sign only depends on the stability of the light ring. This means that if you go back into the diagram, if you have an unstable light ring, then outside of it, radially outside of it, you have only unstable time-like cyclic orbits. Whereas in the case of the stable light ring, the inner region is a region always with stable time-like cyclic orbits. So this is the two main results for this part. Then with these two results, you can then use it to prove that this is in fact the structure that you always see for these two types of objects. So regarding the first one, the ultracompact horizontal object, the region between the stable and the unstable light ring will always be a region without time-like cyclic orbits, because beta will always be negative there. Because in order to show this, if you want a different region between the light rings, beta must be positive to have another type, to have time-like cyclic orbits there. And by continuity, beta must go from negative to positive. So this means that at the radial coordinate, beta will be equal to 0. And like as we saw before, when beta is equal to 0, we have a light ring. But here, if you only impose that these two light rings exist, then the region between them must always be a region without time-like cyclic orbits. In order to have a different type of structure, you need more light rings. and that region must always be a region without time-like circular orbits. In a similar way, for the case for the black hole, you can see. Sorry.
Just to make it to have it clear. Okay. So you're saying basically that if I find an unstable light ring, then I cannot find a stable. Sorry. If I find a stable. Okay. I lost it. Basically, okay. This is saying that if I find an unstable light ring, I cannot find a stable. The radius. No, because otherwise you have a conflict between the.
No, here is just to say that if you have an unstable light ring, then this happens. The outer region is unstable for time-like circular orbits. In the inner one, you don't find anything. For the stable, is basically the opposite. What I'm saying in this part here is that imagine that you have a compact object with these two light rings, only these two, one stable, one unstable. In order to have a different type of structure between the light rings, without being this region of no time-like circular orbits, you need more light rings.
Yes.
That's the idea. So this basically shows that the region between the light rings is always a region without time-like circular orbits. When you have a stable inner one that is stable and the outer one that is unstable. Well, in the same way, you can say that in the case of the black hole, the region between the horizon and the unstable light ring is always a region without no time-like circular orbits, because again, you need more light rings in order to have a different type of structure by continuity of that beta function. So this is the main result of my first part. And what I want to talk now on this second part is try to see this for exactly some solutions. And I will show you what solutions we consider. And at the same time, also consider the efficiency. So here we start the second part. So what is the efficiency? Very briefly, the efficiency is just an estimate for the amount of gravitational energy, which is converted to radiation, as a time particle falls from infinity up to the last stable time-like circular orbit. So we have like a particle that is falling, losing energy for some reason, and reaching, going all the way up into this last time-like circular orbit. So this was already done, for example, for Kerr. And for Kerr, these are well-known results. When you don't have spin, partial case, it's 6% difference. So the efficiency is 6%. And as you increase the spin, the efficiency grows from 6 to 42%. So that's a maximum for the Kerr case. And as we'll show here, for the solution that we consider, you can have much more efficiencies than for Kerr. So I also said that it's the last time-like circular orbit. So here I could say the ISO, which is the most obvious thing to choose. But that's what happens, for example, in Kerr. In Kerr, we have an outer region that is stable, so this region here. And as you go close to the Kerr black hole, you reach a region of instability. And there is where you define the ISO. So basically, there's a change in the sign of the radial stability. And the ISO is exactly when this quantity is equal to 0. However, if you consider very generic ultracompact objects, either horizonless or with a horizon, you may find several solutions when you try to solve that the second derivative is equal to 0. So in order to account for that, we defined the marginally stable circular orbit as a solution with the largest radii, such that the second derivative is equal to 0, and the third one is negative. This is here just to impose that the outer region is a region with stable time-like circular orbits. However, if you remember from the beginning, when we obtained the expression for the angular velocity, we have this expression where we have this C function. And this is C function, as you can see, it may or may not be always positive. If there's some solution where there's some region where this C function is negative, then what happens is that the angular velocity starts to be complex. And what you find is that in that region, you do not find any type of circular orbits, neither time-like, neither null, neither space-like. So you could have something like this. You have in a region with no circular orbits at all, where the C function is negative, that is connected to a stable region. So with that, you could also define some type of ISO. So we call it, in this case, an ISO, which is either the solution with the smallest radii where this happens. So c equals to 0, and radially, slightly radial above, you impose that there are stable circular orbits, and it's the second equation. Or in the case where you find several zeros for the second derivative of the potential, you consider the one that has the smallest radii. So it's the one that is closer to the central object. So what this means in the end is that we have two types of orbits that we want to study, which is the M-scope and the I-scope. For all the solutions, we search for both of them. And if they are the M-scope and the I-scope, we compute the efficiency there and then compare the results, for example, with Kerr. That's the main idea of this second part. So before I start showing the results, let me just give us a brief history, let's say, about the numeric solutions that we obtained throughout my PhD. The main idea is always the same. You start with an action for a theory. It can be anything that you want to consider. You then define an ansatz for the metric and the fields, if there are any. With that, you define the ansatz functions within the metric and the fields. Then you can obtain the equation of motion for these ansatz functions. As well, you can also define the boundary conditions, depending if you want, for example, asymptotically flatness, some symmetries, and so on. After that, we use the PDSol/GATSol solver, that some of you already are well known with that. And finally, we obtain a large set of numerical solutions. So here I have an example of a work that we did that I will also mention in a bit. So basically here I show you all the numerical solutions that we obtained for this theory. So each solution is this orange square. So here we have around 20,000 solutions. And what we do is that we obtain all these solutions. We try to find the domain of existence and try to find the boundaries of this domain. So here, for example, we have these 4 lines, the red, the blue, the green, and the black. And with that, you can then convert our numerical solutions into the continuum so that you can define this blue region that appears below the orange squares. With that, you can then start to study. So, yeah.
Why is there a difference between GR black holes and static black holes?
So here it's in a model that is beyond GR, and there is this alpha parameter, which is a coupling constant. And if it is 0, you get the GR black holes, and the static ones are just the ones that are not rotating. But I will explain a bit more later on. And well, as I was saying, you can define this blue region, which is the region where you expect to find all the solutions in this theory. And then you can study their physical properties and so on, such as computing the mass and momentum, dimensional spin, the little j, for example, and also some phenomenology that here I will talk about is the efficiency. So with that we can now look into the efficiency for some solutions. So I will mention 2 types of objects: stars, horizonless objects, and black holes. For the stars, there are 2 classes of stars that I will consider. The first one is the spinning scalar Boson stars, where the ansatz for the scalar field is given here. So for these solutions, the morphology of the energy density is toroidal, as you can see. And the second class is the spinning vector Boson stars. So here again, we have the ansatz for the vector field. And in this case, the stars, the morphology of the energy density is spheroidal, it's a sphere. So these 2 types of classes of stars can be quite different. So regarding the first class of stars, I will mention 2 families. So the first one is the Mini-Boson Stars. So they are the solution of the Einstein-scalar-Gauss-Bonnet theory, where we have a scalar field that is complex and massive. And now what I'm showing you is the structure of circular orbits for grade 1, so in rotating. So this diagram appears to be a bit tricky to understand at first time, but let me explain a bit. So what we have here is the maximal value of the scalar field as a function of the radial coordinates. And we choose this particular quantity, this maximal of the scalar field, because it's one of the few that increases as we go from, increases monotonically, let's say, from the dilute regime to the more compact regime. So if this quantity is quite small, we are on the dilute region. So this boson stars are quite dilute, are quite large, and the gravitational effects are not very strong. And as we go to the more compact ones, this quantity always increases. So this means that if you draw a horizontal line on this plot, you are basically considering one boson star solution. So for example, let's say I choose this one with the maximum value of 0.2. What this means, and what you can extract from this plot, is that if you are far away from the star, you are in a region of stability. So you have time-like circular orbits. But as you go in close to the star, you reach the icicle here, where within there is a region of no circular orbits at all. So the angular velocity is complex. You can do this for all the solutions. For example, if you consider now a more compact solution, there is this very small region of unstable time-like circular orbits. So the idea would be something like this here. So if you are far away, you are on the stable region. Then you reach the M scope, where there is this region of instability. But then if you go a bit closer to the star, you again starts to be on a stable region, which is obviously very different from Kerr. And if you go again very close to the star, you again reach the ISO, and within you have this region again with no circular orbits. So now that we understand a bit better the structure, you can look into the sphericity, the efficiency. And here again, we have the maximum value of the scalar field now as a function of the efficiency. So again, each horizontal line is one solution. So for example, if I choose a solution that I showed before, where the maximum value is 0.2, you can see that the efficiency at the I-scope is more or less 50%. So here, we see that the efficiency for the I-scope increases monotonically as we go from the dilute region to the more compact region, and it goes very close to unity. And for the more compact solutions where this M-scope appear, the efficiency is much smaller compared to the one at the I-scope. You can see that it starts around 25% more or less and increases to 30-something%. Now you can do exactly the same for the retrograde orbits, so the orbits that are basically contra-rotating. And as you can see, the structure is much more complicated. Now, the dilute solutions are the same as in the prograde case, but then we start to have this region of instability, and with that appears the M-scope. And then even for more compact solutions, we start to have this pair of light rings. So this light ring is always unstable, and this is always stable. So you can see exactly here the result that I showed in the first part, that when you have the light rings, the unstable one has above it a region of instability, the stable one has within it a region of stable time-like circular orbits, and between them you have a region without time-like circular orbits. So basically, it was from here that I start to see some connections and try to prove that this is actually always happens. And in fact, I prove that. So if you now look at this efficiency, the efficiency at the I is exactly the same as for the prograde orbits, so there's no difference. But now the efficiency for the M-scope firstly appears for less dilute solution, pretty much sooner. And since the M-scope is quite far away from the star, the efficiency is also quite small. It's smaller compared to the prograde case. As you can see, it's 3.5 and decreases almost to 4%, but yeah, it's not very large. Now you can do this type of analysis again for another family of boson stars, mainly the axionic boson stars. So these are, the action is more or less the same. What changes is just the potential associated with the scalar field. That is, this potential is based on the QCD axiom-like potential. Now you have this equation. So this B is just a constant. Mu A is associated with the mass of the axionic particle, and this Fa is the decay constant. And if this decay constant is large enough, this potential tends to the mass one. So if the decay constant is, for example, equal to 1 or bigger, basically these solutions tend to the Mini-Boson Star case, so it doesn't change much. But if you consider very small values for the decay constant, then the self-interaction part of this potential starts to get bigger and bigger, starts to get important. And you can start to find different results. So here we decide to fix the decay constant to 0.05, which is already quite small. So looking at the structure of cyclic orbits for the prograde case, we see more or less the same as we saw for the Mini-Boson star case. The only difference, or the biggest one, is that this region of instability appears sooner. And with that, again, the efficiency at the isotope increases monotonically again, as you go from the dilute region to the more compact region. Although now it has some more curves, it's not as almost linearly as it was for the Mini-Boson star case. But regarding the efficiency for the EMSCO, we see that it appears sooner and also has smaller values compared to the Mini-Boson star case. So here, for example, it's around 15 more or less, and increases to around 25. So in the other case, it started at 25, then increases to 30. So here you can say that, at least in this case, the self-interaction starts to suppress a bit the efficiency. Regarding the retrograde case, we see, again, the structure is very similar as what it was for the Mini-Boson star case. You have, again, the light rings, and again, the region between the light rings is a region without timelike cyclic orbits. And if you look at the efficiency for the ice is the same as for the prograde orbits, but now the efficiency at the EMSCO is again smaller. It appears sooner, and since it's far away from the center of the star, it also has smaller values. As you can see, it's only around between 3 and 4%. Now, you can move on to a different type of star, so the vector boson stars, and here I only consider one family, which are the Proca stars, or the mini Proca stars, if you want to consider. And in this case, it's much easier, because for all solutions, as you can see, for the prograde case, you can find stable timelike cyclic orbits everywhere for all solutions. So here, we only consider the isotope, if you want to call it that, as the center of the star. If you consider the compute efficiency, we see that again, it grows monotonically as you go from the dilute to the more compact region. But here it doesn't reach, it almost reached 100%, but it doesn't go exactly there. For the retrograde case, for most solutions, it is exactly the same as for the prograde case. So most solutions can find stable cyclic orbits all the way down into the star. But for more compact solutions, you first start to see these solutions that only have one region of instability, but then there's these solutions that have two disconnected regions of instability. So if you draw the diagram, you'll get something like this. Obviously, this is not up to scale, but yeah.
So one of the parameters of this Proca stars is the oscillation frequency of the star, right? Mm-hmm. Can you give me like a rough map of what the values of those oscillation frequencies are across the y-axis, in case you have it in mind?
I don't have
that was determines the compactness of the star, right?
Mm-hmm. Yeah, I don't remember exactly all.
So I'm typically working with values of 0.8, 0.9. Mm-hmm. So I don't know if you have in mind whether those values are there or.
I have more better understanding of for the Boson stuff because I work more with that with the Proca ones.
But what's the value for the most compact you have?
I don't remember exactly, but I would believe that this can go very close to 1. At least for the Boson stars, it can. I remember going very close to 1. Okay. But then these last solutions, the compactness decreases a bit, so it's no longer very close to 1, but decreases a bit. For the Proca stars, I'm not entirely sure how that's changed, but I will say that should be similar. So these solutions here probably are quite compact, very close to the compactness of the.
And that means smaller scales, right? Smaller frequencies.
Yeah, because they do the curve. So yeah, it should be on the second branch already going to more angle frequencies. Okay. Yeah, this is all. Basically, the Proca stars are the only case that I didn't obtain myself. The other ones I did, so I'm a bit more comfortable. The Proca stars, we only wanted to see how big, how different they were compared to the Mini-Boson star case, because we already knew that they have this energy density that is a sphere instead of a toroidal shape. So we wanted to see how different the structure would be, and as you can see, it's quite different. So that's the main reason that we also consider the Proca stars, but it's the only case that I didn't obtain myself. So I don't know as well as for the Mini-Boson Star case. So yeah, I was saying, so this solution in particular, you can have these two disconnected regions of instability. So here, for example, we only consider the AMSCO as the one that is the one that is further away from the center of the star. So for example, in this case, if you try to find the zeros of the second derivative, we will find 4 zeros. So obviously it's a bit trickier to define everything in that case. But yeah, going on. So if you look now to the efficiency, again, efficiency at the ISCO is exactly the same as for the prograde case. But now the efficiency for the AMSCO, firstly, it appears around at 20% and then increases. But as soon as the second region of instability starts to develop, the AMSCO jumps quite far from the sun, the center of the star, so the efficiency also decreases quite a lot. However, this efficiency is bigger than the Mini-Boson Star case and the axionic case, so it's bigger than 4%, and the other was between 3 and 4. So now we can move on into the black hole case. For the black holes, I have two families of that we study. So the first one is the Kerr black holes with synchronized axionic hair. So this is essentially the natural black hole generalization of the axionic boson stars. But here we consider the same decay constant of 0.05. And here we have the domain of existence of these solutions. We have the angular momentum as a function of the angular frequency. And this blue region is where you find all the black hole solutions. It's bounded by the axionic boson star line, so the red line, and the existence line in blue here, which basically represents the Kerr black holes that can support scalar clouds. Then the second family is the Einstein-scalar-Gauss-Bonnet black holes, where we have a real scalar field that is linearly coupled with the Gauss-Bonnet term. So, and we have this alpha, which is basically the coupling constant. So here, again, we see the same plot that I showed some slides before, but now I can explain a bit more. So this is the domain where you can find all the solutions. It's bounded by 4 lines. So we have the Kerr black holes, so when alpha is equal to 0. And we have the static black holes where you don't have any rotation. Then we have these 2 lines. So the extremal set is a hairy solutions that have a vanishing Hawking temperature. So they're extreme. And then we have this critical set where it's the last hairy black hole solution before they start to develop negative singularities, or starting to be negative singularities. Because in this theory, there is a minimal value for the area. So there is no connection to flat space or without anything. So that's the critical set. Now, regarding the first solution, the Kerr black holes with synchronized axionic hair, I show you here the domain of existence.
I'm sorry, can I make a question?
Yeah, yes.
The last slide, previous one.
Mm-hmm.
What do you mean by synchronized? It's just like the
yes,
frequency of the star and the hair and the black hole is the same.
Yeah, there is a synchronization in order to have a stationary hairy solution. In this case, mm-hmm. There must be a synchronization between the horizon velocity or angular velocity in that case with the frequency of the scalar field. There is a synchronization between the two. That's the name.
And you don't have this condition for the Gauss-Bonnet black holes?
No, you don't need to. For the Gauss-Bonnet ones, you don't need that synchronization.
Okay, thank you.
You're welcome. So here we have the domain of existence for these hairy solutions, and it's divided into regions. So this region of light blue corresponds to solutions that have a structure that is similar to Kerr's, so only one light string and only one ISCO. And the dark blue region corresponds to solutions with a non-Kerr structure. So it may have different number of light rings or even more disconnected regions of instability. And if you look into the efficiency, so now we have efficiency as a function of dimensional spin. We have the Kerr line, the blue dashed line. So it grows from 6% for the Schwarzschild. And as you increase the spin, the efficiency grows up to 42%. But here you can see that even for solutions with a very Kerr-like structure, the efficiency can grow very close to unity, can be greater than the 42%, and can go very close to unity. Then we also have this small region of solutions that don't have a structure very similar to Kerr, that also have more efficiency than the extremal Kerr case. Then you can do exactly the same for the retrograde orbits. So now we have again this division between the two regions. And the efficiency now for the retrograde case for Kerr, it starts at 6% again, but now it decreases as we increase the spin. But here again, you can see there are both airy solutions with a Kerr-like structure and non-Kerr-like structure that can have more efficiency than the efficiency for Kerr in the retrograde case. However, this doesn't reach the 13% mark, so it's less than the extremal Kerr for the prograde case, if you want to compare those two. Now, regarding the Einstein-scalar-Gauss-Bonnet black holes, the analysis is much simpler because for this case, all solutions have a Kerr-like structure. So here you have again the domain, and here we have the efficiency as a function of the dimensional spin. Now the Kerr line is this red solid line. And we see that if the black hole, the hairy black hole is not rotating fast enough, so dimensional spin is small, then the hairy solution always have more efficiency compared to the Kerr with the same dimensional spin. However, for fast spinning solutions, the reverse happen. So the Kerr solution is now the one that has more efficiency compared to the hairy solution. And the maximal value is attained at the extremal Kerr case. So the maximal value here is 42% for extremal Kerr. For the retrograde orbits, we see that now the hairy solutions are always the ones that have more efficiency compared to the Kerr with the same spin. However, this difference starts to decrease as we add more spin into the solution. Yes?
Is this phenomenology happening because in the GR case, once you cross a given spin limit for the black hole and the particle that it's in volume, at the end of the day, you need to respect the Kerr limit. So you need to release angular momentum.
Well, in this case, you can find solutions that can violate the Kerr limit.
I mean,
it's
the,
only
the GR.
the GR?
As per the red
Okay.
line.
Yes. So one idea that tried to explain this result, we also look into that on the original paper, is that if you compare the linear velocity of the horizon of the Kerr solution with the hairy solution with the same spin, the hairy solutions spin faster than Kerr for small spins, but the opposite happens when you have large spins. So this is probably associated as well as to the comparison between the linear velocities of the horizons. Because we also saw that on the original paper, and we tried to explain with that. So here, probably it's the same reason why the efficiency for small spins, the efficiency is bigger, but then for large spins, the efficiency is smaller compared to Kerr. Okay, so just to finalize, to summarize everything up. So in the first part, I talked about the structure of circular orbits, and I showed that for a very generic stationary asymptotic, asymptotically flat in a four-dimensional compact object with a Z2 symmetry, these two structures is also always possible to see. And with those two structures, I show you that in the case of ultracompact horizonless objects and for black holes, these two structures are also always possible to verify. Regarding the efficiency, for the spinning scalar boson stars, we saw that for the ISCO, it's the same for prograde and retrograde orbits, and the efficiency can grow very close to unity. For the efficiency at the ends, the prograde orbits show more efficiencies than the retrograde ones, and the presence of self-interactions, at least in the case of the axionic potential, this tends to suppress a bit the efficiency. For the vector boson stars, so the prograde stars in this case, again, the efficiency at the ISCO is exactly the same for the prograde and the retrograde orbits. And it's also possible to find stable circular orbits all the way down up to the center of the star. That does not happen for the boson star case. And due to that, the efficiency also can grow monotonically to values close to unity. Regarding the efficiency at the M score, it only appears for the retrograde orbits. So for the prograde ones, you don't have this M score. This happens because in the retrograde ones, you can find some disconnected regions of unstable circular orbits. And due to that, and since it appears far away from the star, the efficiency can drop to very small values. Regarding the black holes, the efficiency for the black holes. For Kerr black holes with synchronized axionic hair, we saw that there are some solutions that can have a structure that is similar to Kerr's, and others that can develop new regions of instability or a different number of light rings that gives those solutions a non-Kerr structure. For the prograde orbits, we saw that the efficiency can be much larger than the maximal efficiency for Kerr and can go very close to unity. For the retrograde orbits, we saw that the efficiency is much smaller compared to the prograde orbits, but they can be bigger anyway when compared to the maximal Kerr value for the retrograde case. For the Einstein-scalar-Gauss-Bonnet, the analysis was much simpler because all solutions have a Kerr-like structure. And we saw that for the prograde orbits, if the dimensional spin is small enough, the efficiency for these airy solutions is bigger compared to Kerr for the same spin. But the opposite happens if you consider solutions with large spins. For the retrograde orbits, on the other hand, the efficiency is always larger than the Kerr's one with the same dimensional spin, but this difference starts to decrease as we increase the dimensional spin. Now, just to mention future works that we are trying to finalize, let's hope in 1 month or two, this paper will get out. So one of them is regarding the angle stability. So all this work was only focused on the radial stabilities. But you can also have stability of perpendicular to the equatorial plane, because you can perturb it in that direction, try to see if it's stable or not. So what we found is that the angle stability of the light ring also imposes the angular stability of the timelike circular orbits. So instead of only having 2 cases, we will basically have 4. Either the light ring is fully stable, so stable on the radial and angular part, or fully unstable, or a mix between the 2. And what we found is that is these 2 cases plus another 2. So for the full stable light ring, the inner region is fully stable for the timelike circular orbits. If the light ring is fully unstable, the outer region is also fully unstable for the timelike circular orbits. And then we have the mixing between the 2, that if you have a radially unstable but angularly stable, outer region is also like that for timelike circular orbits, and vice versa for the radially stable and angularly unstable light rings. So condensing everything up, what this means is that the radial stability of the light ring determines the possibility and the radial stability of the timelike circular orbits. So it defines the stability and where you can find it. The angular part, the angular stability, only determines the angular stability of the timelike circular orbits. Only that, not the position, only the stability. Also, if you consider, or if you introduce the energy conditions, you can find that this case of the fully unstable case is not possible. So you have to violate energy conditions if you find this type of structure. Another work that we are trying to develop and to finalize as well is regarding the extreme mass ratio and spires. So this is, for the ones that don't know, consider a very large black hole, for example, or object in the middle, in the center, and then you consider a very small one outside of the object. And then you try to see how is the time evolution of that small object by considering that it's losing energy through the quadrupole formula for gravitational waves. And with that, you can do this time evolution, try to see how the radial coordinate changes also, and you can also extract the frequency of the gravitational wave produced. And there is some work already done about this for Kerr black holes with scalar hair. So these are the natural black hole generalization of the Mini-Boson stars. So you don't have the axionic potential, you only have the mass one. And this was done by Donev and Corollaries and collaborators. where they consider these solutions on the region where you can have quite a lot of error. So they are most likely unphysical, or they don't exist in the universe, but they also show quite interesting results. Mainly that's if you do the time evolution of the radial coordinate, you can see the comparison between the Harry solutions with Kerr. And you can see that it's quite different, but mainly the frequency associated to the gravitational wave for Kerr always increases, as is expected. You expect the frequency of the gravitational wave to increase and to have the chirp. But for this Harry solution, you can see that it increases in the beginning, but then it stabilizes more or less on the same frequency during a part of some time slot. And then when you get close to the icicle is when you have again the chirp. So these two results are quite different. So in 10 years or something, a bit more, when ELISA is operational, this would be very easy to detect and to see if this type of Harry solutions also exist. But what we want to study is more realistic Harry solutions, in the sense they are more Kerr-like. So we are looking at solutions with dimensional spin equal to 1, so that to compare to the maximal Kerr case. And here, for example, I obtain 50,000 solutions on this, only this region, to give or to have a well-defined line for j equal 1. So in that case, we have two lines. We have this orange one that grows from maximal Kerr to the boson star. So here, the hairiness of the solution increases as you go alongside the line. So here you can find very different types of results. You basically see an evolution that starts with curves and then changes as you go close to the boson stars. But more interestingly, is this red line, where the hairiness of these solutions does not go above 10%. So this means that the mass associated, the mass outside of the horizon in the scalar field does not exceed the 10% mark compared to the total mass of the black hole. And even in this case, we see that there are very different results. For example, if you compare the cutoff frequency of the gravitational wave produced compared to Kerr, with the same spin and the same mass, there is quite a large difference, so around 80% difference for some solutions, which is very, very different, even for solutions that are more or less close to Kerr. So we start to see that these Harry solutions can be quite different. But well, let's hope that in 1 month or two, this paper will get out, and let's thank you.